Hi there. In today's video, we're going to be introducing two concepts that are going to follow us throughout the rest of this course, throughout this semester. So they're going to pop up from time to time, and we want to make sure we know what they are when they show up. So the first concept we're going to explore is something called a linear combination, and then we're going to look at some homogeneous systems. So let's begin by defining what it means to be a linear combination. V is a linear combination of matrices, capital X1, capital X2, capital Xn, if there exist scalars, lowercase a1, lowercase a2, lowercase an, so that V is equal to a1 x1 plus a2 x2 plus an xn. Or if you prefer summation notation, V is the sum of ai xi. And here we've defined what it means to be a linear combination. Now, before we kind of talk more about this definition, let's think about what our experience with linear functions has been so far. So when we've looked at our systems of linear equations, we've had things like, just going to make one up. Okay, so we have 2x1 plus 2x2 plus 5x3 is equal to 7. So we've had linear equations like this so far. Now, when we write our linear equations like this, our assumption is that we plug in numbers for x1, x2, and x3 in order to get the 7, right? So our variables in this case are representing numbers. A linear combination of matrices is the same thing, except instead of numbers here, our objects are matrices. So we might have 2 times a matrix plus 2 times this other matrix plus 5 times this third matrix is equal to a matrix. That's all that a linear combination is going to be. It just means you have some scalar times an object plus a scalar times another object, yada, yada, yada. Because matrices have become our objects, we're going to start to manipulate them in the same ways that we've been manipulating numbers all our lives. So we're accustomed to linear equations. So now we're just going to have a linear combination using where the variables represent matrices instead of numbers. So let's do a couple of examples of writing some of our parametric solutions that we've already seen as linear combinations of matrices. For our first example, we're going to look at a matrix that we saw in a previous example, and we're going to write the solutions to this system as a linear combination of matrices. So to begin with, we have to find the solution to the system. So in this case, let's use x1, x2, x3, x4. So we'll use those. So there's no pivot position for x4, which means that means our x4 is going to be our parameter. So I'm going to set up a list here. So x4 is our parameter because it has no pivot position. So I'm going to choose to use t for this. Now, if you want to do these next couple of things in 2 steps, you can. If you want to do them in 1 step, you can as well. So to demonstrate what it looks like in 2 steps, that's what I'm going to do for the first one. And then I'll do the others in just 1 step. So I like to kind of go my way up here in case I need to substitute in any parameters or previously defined variables because of how the leading values go in our matrix. So the first equation I'm going to look at is this one. So this tells me that x3 plus 3x4 is 2. But to save some time, we know that x4 is t. So I'm just going to write t there instead of x4. And to get x3 by itself, I'm going to subtract 3t from both sides. So this means that x3 is 2 minus 3t. And there we go. So this would be sort of a two-step process where I substitute in and then solve for the variable. As you become more comfortable with these, you start to notice the patterns and take some more shortcuts. So for example, I know that this is going to be x2. I have no x3, and I have 2x4 or 2t. So essentially, in order to solve for this variable here, I'm going to have to subtract this one to bring it to the other side. So I know this is my constant value 6, and then I'm going to subtract 2 of x4, or in this case, 2t. So I can go directly from this line to my result here. I can do the same thing for the first row. I have -1. I'm going to have to subtract this to move it to the other side. And it's in the column for x4, which is t. So this will be my parametric solution to this system. Next, we want to write this as a linear combination of matrices. So to begin with, I'm going to set it up as a matrix, and then we'll write the linear combination. So I've got my -1 minus 4t, 6 minus 2t, 2 minus 3t, and t. And the way that I like to think of this when I go to write this as a linear combination of matrices is I think, okay, it's basically like splitting out your liked terms, essentially. So I'm going to take, for my first matrix, anything that is not attached to a t. So all just the constant values. So here, that's going to be -1, 6, 2. And then because we only have something with a t here, that means we're going to get a 0 because nothing is not attached to t. So we have -1, 6, 2, and 0. Next, I'm going to add the matrix that is made up of the t's. So this is -4t, -2t, -3t, and t. And then to finish it off, it's pretty standard to factor out that t and write it in front of or behind the matrix. So I'm going to get -1, 6, 2, 0 plus t times -4, -2, -3, and 1. So this matrix here is made up of the coefficients of the t here. And this would be my final answer. Okay, so this is my linear combination of matrices that's going to represent my solution to the system. Again, think about like y equals mx plus b, right? So we have some number plus some number times x, our variable, that's like a normal line. So that's what's going on here, except instead of the sum numbers, we have a matrix. So we have our solution matrix equals some matrix plus another matrix times some number. So that's all a linear combination is. That's what's going on here. So now that we've done an example together, I'm going to put one on the board for you to try on your own, and then we will go through the solutions for that. Okay, so for this example, you're going to try out the same thing just with this new matrix. This is the matrix we had back in example 10. We had to solve a system, and this was our final matrix in reduced or echelon form. So pause the video, solve this system, and then write that solution as a linear combination of matrices. And when you've got it all set, unpause the video and we can check your work. All right, how did we do in solving this problem? So this problem had 2 parameters, unlike the last one, which only had 1, but our process is identical. So I started out by writing my solution for each variable. In this case, z and w lacked a pivot position, so those were our 2 parameters, and everything else was in terms of them. And then I just basically took these values and threw them into a matrix. This first one here, we'll notice there's a 0 in the last and in the second rows because that's where we had our parameters, so there was no constant number there. Then for the s's, these were the solutions that just involved s, so those were just the 2 rows. everything else is going to be a 0. And then similarly for t, there's no t in the second row, so we have a 0, and then everything else has the coefficient of t. There we go. That's our writing solutions as a linear combination of matrices. So the next topic we're going to talk about are a special type of system of linear equations called a homogeneous system. And in a homogeneous system, the only thing that makes it different from a normal system is that this last column is always zeros. So in other words, every equation in the system has to be equal to 0. So let's write a couple of formal definitions, and then we'll do some examples of finding solutions to homogeneous systems of equations. Here's our definition for a homogeneous system. A system of linear equations is homogeneous if each entry of the constant matrix is a 0. And in other words, those BIs are 0. Now, I've got this notation here with this upside down A. Upside down A means for all or for any. And in the last definition, I forgot to mention, although I used it, this backwards capital E means there exists. So when you see an upside down A, that's the shortcut for all or for any, and this backwards E is the notation for there exists, just to kind of make it easier, more concise to write our definitions of things. So an example of something that might be a homogeneous system of linear equations could be like x minus 4 equals 0 for y. I should put for y there. And let's go with 2x equals 0. This is just a basic homogeneous system. And what makes it homogeneous is we have these zeros here. Now, something that's going to happen for no matter what homogeneous system you have, well, in this case, because I have two variables, I'm going to have a 2 by 1 matrix being my solution. If I had 3 variables, then the matrix 0, 0, 0 would be a solution, right? So however many variables you have, that's going to be how many rows you have of zeros for your solution. And that's because 0 minus 0 is 0, and 0 is 0. So no matter what homogeneous system you have, the matrix that is made up of only zeros is going to be a solution. So something we might be interested in is that the only solution, or can we find other solutions that aren't that? So to help us be able to do that, we're going to define what this kind of solution is, give it a name, and then we'll give a name to those solutions that don't look like that. Here's our definition for those types of solutions. So all homogeneous systems have a trivial solution when each of the xi's is 0. So x of I is 0 for all of those i's. And any other solution to the system is going to be called non-trivial. Now, the word trivial here doesn't mean like unimportant. It just means like, yes, it's always there. I don't have to do any work to find it. It's trivial work to do in order to find it. So non-trivial means we're going to have to do some work in order to find those solutions. So how about we do an example of doing that work? Let's find all of the non-trivial solutions to a homogeneous system of equations. When you see words like find non-trivial solutions, or if you see homogeneous system of equations, don't let that, send you into a panic. What the heck does this mean? It just means we're going to solve this system like we normally would. So I'm going to use some Gauss-Jordan elimination to solve this system. To begin with, we're going to write the augmented matrix. 1, 5 for our first column, -3, -15, 1, -5, and then our column of zeros, because this is a homogeneous system, so we have zeros here. I'm going to, well, since I have a 1 here, I'm going to subtract 5 copies of row 1 from row 2 to get a 0 underneath. And then I'm going to rewrite it. So while I'm rewriting it, how about you rewrite it, and then we'll check our arithmetic after. How do we do? So in my second row, I got everything except I got a -10 here. Everything was a 0 except for that spot, which means I have no pivot position in the second column. So we are going to get a parameter. And I'm going to multiply the second row by -1/10 to turn this into a 1. Row 1 stays the same. Bottom row, we're just going to get this one here. Then, because we're using Gauss-Jordan elimination for this problem, that means not only do I need zeros below my leading entries, but I also need zeros above. So I'm going to have to take this row and use it to get a 0 here. So I'll do that by adding negative row 2 to the first row. So because we have zeros everywhere else, this is the only value that's going to change, and it's just going to turn into a 0. All right, cool beans. So we've got our matrix reduced in reduced row echelon form. So let's use that to write our solution. And because we just learned it, let's write our solution as a linear combination of matrices to boot. So I'm going to have x1, x2, and x3. And as I mentioned before, I like to move from right to left or from bottom to top. So this is telling me that 1x3 is 0. I have no pivot position in the second column, so x2 is going to be my parameter. In this case, I'm using t. And in my first row, this is x1 minus 3x2, or x1 minus 3t. So I'm going to add that over to the other side. There's already a 0 here, so that's fine. So I'm going to get 3t. If I write that as a linear combination of matrices, that's going to be, well, let's just start out, 3t, t, 0. And there's only 1 here, so let's just basically factor out that t. And there we go. Now, if we wanted to, kind of be a little extra, we could do one more step, which would be to write the following. In this case, I've basically just added 0 to it. All that this is doing is saying that my constant matrix of a solution would be zeros because I had no constant values when I solved. They were all in terms of the parameter. So these are the non-trivial solutions because if I pick any number for t that's not 0, I'm not going to get the 0 back. So if t is 1, I get a solution of 3, 1, 0. That's not 0, 0, 0, so it is a non-trivial solution. So that's basically all it means is when you see find all the non-trivial solutions, you need a parameter for your solution, so you get things that aren't zeros. If you solve it and you don't get any parameters, that means that there are no non-trivial solutions to that system. The only place where they intersect is like the origin in that space. Now, it turns out that these types of things that we're adding together in our linear combination of matrices are going to be important for us to talk about. So, as always, we're going to give important things a name. So let's examine a follow-up question to this example. Our follow-up question is this: what is the free variable in that last example? And what is its corresponding matrix? So this is our solution, a linear combination solution that we had written before. And the free variable, you'll remember, is the variable that was assigned the parameter. So in this case, we had 1t in the second row. So that means our free variable was x2. when we say this, the corresponding matrix, what we kind of mean by that is here's our parameter, the t. This is the matrix that it's attached to. So it's like corresponding matrix. So that is 3, 1, 0. And that's it. Now, this corresponding matrix here is going to be called a basic solution. And you might be wondering, this is the basic solution, but it was the free variable, not the basic variable. So why don't we call it the free solution instead of the basic solution? Well, the terminology comes from your basic solution is the one that doesn't change to your system. The free variable is going to have a basic solution when you set all of the other parameters equal to 0. So basically, if that was the only parameter in existence, what would be its matrix? So that's kind of what's going on in the background there. We're just going to have to, if it helps you to remember free variable basic solution, not basic, then that's going to be how we remember it. But what's going to be nice is that we can use these basic solutions or these values here to help us find solutions to homogeneous systems. So we're going to write a note, and then we have one last example to do for this video. Note 5 says that any linear combination of the basic solutions to a homogeneous system is again going to be a solution to the system. And that kind of makes sense because we had our zeros, however many we have of them, and then we have plus a parameter times our next matrix, whatever that is, plus a parameter times its matrix, whatever that is, and so on, right? So a linear combination of the basic solutions would just be that. It's going to be something times that first basic solution plus something times that second basic solution. Now this works for a homogeneous system because this matrix here is just made up of all zeros. If this wasn't made up of all zeros, then this wouldn't work because we would have something else we'd have to add to the whole thing. So in this example, we have a system of linear equations, a homogeneous system, and we're told that it has basic solutions of x1 and x2. Now, to try and keep my capital X's different from my lowercase x's, you might have noticed I've started writing my lowercase x's kind of as more rounded. So these are going to be my lowercase x's, and then the normal x's are going to be my uppercase x's, just to make it a little bit easier to tell in the notes. So this is a capital X1, and this is our first basic solution, and then this is our second basic solution. So if I want to find 3 non-trivial solutions, all that means is I have to make sure that I do a linear combination of these two, and the coefficient is not both 0 for each of them. So in other words, pick a number. I'm going to pick 4. I'm going to do 4x1. And since I have a 4 here, I'm going to do none of x2. So I'm going to multiply each of these values by 4. So that's going to be -1, -1, 4, and 0. Plus 0, there's nothing else there. So that's it. This is one non-trivial solution to this system here. And if we wanted to check it, we can plug in those numbers and see if it works. So we can do the same thing for this one. Let's just reverse those coefficients. So let's say I have 0x1 plus 4x2. This time I have none of these, and I have 4 of these. So that'll give me 0, -4, 0, and 4. So here we found 2. Let's find one more because we were told to find 3. Again, it doesn't matter what numbers you pick as long as they're not both a 0. So let's say I go with -8 x1 plus 3x2, just to do something a little bit different. So if I take -8 and I multiply it by this matrix, that's going to give me a 2, a 2, -8, and 0. And if I take 3 of the second matrix, that's going to give me a 0, -3, 0, 3. And now I just add them together to get my final answer. So really what I'm doing is this. And in the end, I get 2, -1, -8, and 3. So this is a third non-trivial solution to the system. Let's check this one because this one looks weird, right? So this is going to give me 3 times 2. So that's going to give me 6, -1, -8, plus 3. So I get 9 minus 9 is indeed 0. So that one checks out. And in my second equation, 5 times 2 is 10. Minus -1 is +1. Plus -8 is -8. And then -3. So let's see, this is 11. That's -11. We get 0. So this is another non-trivial solution to this system. All right, so that concludes our videos for the first week. Next week, we're going to start doing operations on matrices. So we've kind of secretly already started doing that a little bit with our linear combinations, but we're going to start thinking of matrices as objects and stop thinking of numbers as objects. Numbers are just going to be, values that we can make matrices bigger or smaller by, but the matrix itself is going to be our primary object. So just like when you're a little kid and you learn how to add and subtract numbers, and then you learn how to multiply and divide them, and then you put them into equations and functions to solve, that's where we're headed. So we've got our matrices, so we're going to learn how to add or subtract them. We're going to learn about multiplying them and putting them in equations and functions and solving, where those are our answers instead of just a single number. So I'm looking forward to sharing that all with you next week. In the meantime, have a wonderful day, and yeah, bye.